Okay, our next speaker is Professor Tamás Ungár from the Department of Material Physics at the Eötvös University in Budapest in Hungary. He's going to continue this theme of microstructure by line profile analysis. Line profile analysis.
Ladies and gentlemen, first of all, I have to thank Bill and Kenneth for their very kind invitation, and I was obliged to do this presentation. Believe me or not, at the end of this presentation, I hope you will have the impression that we intensively negotiated with Matteo to build a double lecture, but we didn't. I will continue where Matteo finished, more or less. Whose fault is it? That was the title given by Bill. There could be another title saying the effect of faulting and twinning on the profiles of diffraction peaks. Twinning is well known to all of us. This shows TM micrograph of a nanocrystalline particle in a nickel-titanium shaped memory material, and on the right-hand side you see the diffraction pattern, and what you see in a TEM micrograph, and we know very well that if you have planar defects in a material, then you observe streaking. That means the diffraction is elongated in directions which are perpendicular to the planar defect. This is another example, again from the same system, nickel-titanium shaped memory alloy, and here you see that the twinning is a planar defect on the two sides of which the crystals match perfectly. This is just to show you how beautiful micrographs you can get in a twinning or in a twins structure. These people have started from an amorphous state, and they de-vitrified the specimen and obtained these lovely little gemstones, which can have this pattern if certain diffraction spots are selected and dark field images are made. You can very clearly see the twin planes. Nickel-titanium shaped memory alloys deform by twinning, and you see how the twin sequence can be extremely large. The distance between two twin layers is very small. This is a very old micrograph stemming from less than 1976. Actually, I took the reference from the book of Kali. Probably many of you know this book. And there is no reference to a paper published by Kutzmann, who made this high-resolution TEM probably in the 60s, along with the diffraction pattern, and you can see this beautiful streaking due to these parallel planar faults in this structure, streaking normal to the fault planes. If you go back to the book of Warren, you see this figure. It explains you in a very straightforward manner how planar defects can be systematized. In an FCC structure, the sequence is the well-known ABC, ABC along the close-packed plane. And if you take out a plane, then you produce an intrinsic stacking fault. If you push in a plane, you obtain an extrinsic stacking fault. And if you just reverse the sequence in direction, then you obtain a twin. This is all very nice for close-packed planes, especially for FCC or HCP materials. But what about the metals or their alloys if the structure remains basically the fundamental structure, like magnesium, titanium, zirconium, beryllium, zinc, etc.? These are very common structural materials, today very intensively investigated by many different techniques. And it turns out that in these materials, which are our important structural materials, twinning or the planar faults do not follow the simple rule. Not the close-packed layers or planes are producing these twin faults. For example, in a titanium aluminide, which has the DO19 order structure based on an HCP lattice, you can see that prismatic planes, not the close-packed planes, but prismatic planes or pyramidal planes can be faulted, twinned. These are optical micrographs. This is another optical micrograph taken from the same paper, showing very beautifully the pyramidal plane, which plays the important role in twinning in hexagonal metals. There is an important difference between twinning or faulting on the closed-packed planes and twinning on other planes like the pyramidal planes in hexagonal materials. You can see here the reciprocal space of the mother crystal and the twin crystal, and what you observe is that none of the diffraction positions coincide except those which are along the twin plane. And this, as you can find in the textbooks, is so-called non-merohedral behavior. This is another example of titanium, of a titanium alloy, which is very commonly used in engineering, and you can see these beautiful pyramidal twin lamellae in the dark field image and also in the bright field image. This is a cartoon showing how twinning on the pyramidal planes are occurring. This shows that this is the C-axis, which turns almost perpendicular to the mother crystal. And here again, you can observe that these diffraction spots in the mother, in the matrix, and in the twin crystal will never meet again, unless some very odd conditions for the C/A ratio are satisfied. And this we call non-merohedral. If twinning is on the closed-packed planes, then the mother and the twin crystal are partially merohedral because all third layers in the reciprocal space coincide for the mother and the twin crystal. So let me switch now to a little bit on the philosophy, which actually Matteo has shown beautifully in the previous lecture, but let me just go through a few points. We have seen in the previous lecture that we can call it a bottom-up approach because we start from physical models of the lattice defects. The profile functions which we are using in our evaluation are created by theoretical methods which are based on real lattice defects. We have seen a long equation containing many different terms, each corresponding to different lattice defects, which we see in a micrograph, for example, in a TEM micrograph. Actually, this bottom-up approach relies very much on the TEM work, which so many people have been done. The diffraction pattern is then fitted by patterns which are constructed or by using these defect-related profile functions, just as Matteo has shown that. Now the philosophy, just to repeat that, we have a measured pattern, we have physically modeled profile functions for the size, for the strain, for planar defects, planar faults, and we have instrumental effects and a background. This is what goes into the physical modeling. This is what we determine experimentally, and this is what we measure, and we want to compare the two by some mathematical methods, and we end up with some physical parameters. We have seen before that strain can be characterized in terms of dislocation densities, or you need another parameter telling you about the dislocation arrangement. Dislocations can arrange in very different manners. I don't want to go into detail at this moment. And there is the strain anisotropy, which is well known to all of us in crystallography and in all Rietveld approaches or codes. Strain anisotropy is a well-known phenomenon, and this third parameter is taking into account strain anisotropy based on, it can be based on a dislocation concept. The size can only be described by minimum 2 parameters. Matteo has shown that you even can have more than 2, but 2 is the minimum. Because if you have a size distribution, you have to say where the size distribution is sitting, and you have to say something about the breadth, the distribution, the spreading of the size. And at the end, if you are able to say something about the planar defects, you have an additional parameter telling you the density of these planar defects. Strain, let me just come to strain broadening very briefly. It is concentrated in the parameter the mean square strain. This has been derived in the book by the works of Warren, or even before by Wilson. Many people have been contributing a lot to that. The essence of strain broadening of a diffraction profile is given in this formula, which is the strain Fourier coefficient, which contains the mean square strain. And now the question is how we model the mean square strain. And one of the best models we have today is this one, which was developed by the late Krivoglas and late Wilkens. Well, it started in the 50s and ended it in 1970, and it contains actually few parameters. It contains the dislocation density, a factor which takes into account the mutual orientation between a dislocation is a line. So it is the most anisotropic lattice defect what you can think of. And it has to be characterized by its strength, which is the Burgers factor, its line vector, which tells you the orientation, and the elastic constants of the material also play a role. That is all in this factor C. This is the Burgers factor. And there is a function which tells you the functional form of the mean square strain. Whenever you have done a Warren-Averback analysis, you always have had to realize that the mean square strain is not a number. It depends on the Fourier coefficient, on the Fourier parameter. This is what I told you before. Now this eta parameter in this f eta function contains the Fourier variable L, and this is the, so we call this effective outer cutoff radius of dislocations. It's not a very complicated parameter. It tells you how far the strain fields of a dislocation can reach, because if you have a dislocation ensemble, like you can think of a dislocation gas, the many dislocations, they screen each other. The strain field will not go infinitely far, but it will concentrate around a certain region, and this we call effective outer cutoff radius. Now this is the functional form of this Wilkens function. The blue curve is the true function. It cannot be given analytically. It contains two asymptotic regions. For small Fourier variable values, it is logarithmic, and for large Fourier variables, it is hyperbolic, and the two are combined to give this function. So this is very essential for the strain broadening if you want to make it into a profile. And this is the profile function normalized to the maximum and normalized to the half width. And you can see that if it can have two extremely different shapes, it can have a long tail or a short tail, and with the long tail, it means that the strain field of the dislocations is concentrated around the dislocation, doesn't reach very far. Whereas if the strain field reaches very far out, then it is more like a bell shape. It is more like a Gaussian. It is never a pure Lorentzian and never a pure Gaussian. It is always between the two. And this is perhaps one of the points which has to be treated very carefully when you apply a top-down approach, like, for example, when you do a Rietveld analysis and you end up with a pseudo-void function which contains a Lorentzian and a Gaussian part. You actually shouldn't say that the Gaussian part is produced by microstrain, because the strain can have a Lorentzian peak shape. The strain profile, just want to summarize, is the Fourier transform of the Fourier coefficient. So this is behind the integral, you have just the Fourier coefficient, and that is back inverse Fourier transformed to produce the strain profile. The size profile is somewhat more simple, although Matteo mentioned that you can have a very complicated shape or size distribution. You can have a bimodal or many different shapes in your specimen. If your size distribution is not very complicated and you can describe it with one size distribution function, let's say a log normal size distribution, then you end up with two variables. One gives you where the size distribution sits, and the other one what the distribution of your size profile is. Now, so the bottom-up approach of this line profile analysis is based on physically modeled profile functions. Now, what about the profile functions corresponding to faulting and twinning? We heard a little about that in Matteo's presentation. He was referring to the DIFAX software. I would like to show you how the profile function for faulting can be conceived. Just to define what happens if you have planar defects. You have the crystal planes, these straight lines. This is the corresponding diffraction vector pointing into a diffraction, into a fundamental diffraction spot. And let's say this dashed line is the fault, the planar fault. Then streaking will be observed in reciprocal space, as we have seen in the micrographs and the diffraction patterns. Now, we can introduce a coordinate system, especially because in the hexagonal materials, if twinning is on the pyramidal plane, then you cannot introduce a simple coordinate system. You are bound to use, or it is advantageous to use a Tricklin system, which can be correlated with the streaking in reciprocal space by the third reciprocal space vector lying along the streaking direction. Now, here I show you two different diffraction profile sets of diffraction profiles, which were calculated by the DIFAX software. We have seen that reference already in the previous presentation. It corresponds to twinning on these pyramidal planes with 2% twin density and 6% twin density. The red curves are broader, the blue curves are narrower. They are far apart from each other. Along the, this L is now the third reciprocal lattice variable in the streak direction. You can see that these are just normal thin diffraction peaks, broadened slightly. These are not line profiles yet, because the line profiles are measured in the direction of the diffraction vector. So overlapping peak, the next point I want to show you, that overlapping peaks along the same streak produce an asymmetry. If the fault density is not too large, then the streaks are not very long. And if the corresponding reciprocal lattice points are far from each other, then the streaking will not overlap. However, if the reciprocal lattice points come closer to each other, or the twin density becomes high, then these streaks will overlap. And this overlap will produce an interference effect, which will make the diffraction profiles asymmetric. You see here so-called subreflections. Subreflections, that means they correspond to one certain orientation in the crystal, where in this reflection you have you can have this subreflection. The twinning plane is this pyramidal plane, and you have here along one particular streak or one particular reciprocal lattice line, you can have these two peaks close to each other. And if the twin density is high enough, they will strongly overlap, the streaks will strongly overlap and produce an asymmetry. It turns out that the asymmetry can be described by a symmetrical profile plus the same symmetrical profile multiplied by a linear function, giving this asymmetry, and the blue curve will be the sum of these two. If I'm showing only the left-hand profile from the previous graph, then you can see this asymmetry. This tail on the right-hand side is much longer than on the other side. The intensity distribution in the streaks can be formulated as a function of the twin density. You have to make a description of the twin probability. If the twinning is an independent effect, the twin boundary does not influence the position of the next twin boundary, then you end up with a bimodal distribution, which will look like that. And using this, you can produce, there is a long calculation, but at the end, you end up with this intensity distribution in reciprocal space along the L variable, that is the streaking line. You have the symmetric profile is with the number 1, and the asymmetry is given by this term in this sum. But main point is that this is a Lorentzian type function. The full width half max in the trickling system in reciprocal space can be written in this form, where beta is the twin density, and this d sub trickling is a constant. This Lorentzian type function, it turns out that this constant is 5.775. It seems to be a magic constant, but it can be shown that this is a universal relation for twinning, apart from whether it is in the closed pack, whether twinning is on the closed pack planes, or whether it is on the pyramidal planes. With this formula, we arrive at a profile function for twinning for any plane in the triclinic system. L is always indicating that it is not yet a line profile. Now the next step will be to produce line profiles. Perhaps one more important point. In this representation, in the triclinic system, the profile functions are identical. They have no HKL dependence apart from the asymmetry. It will be the transformation into the G direction, that means when we produce the line profiles out of these folded profiles, which will produce the HKL dependence, which will also enable us to extract information about the fold properties, fold density, and fold type from the peak broadening. Broadening in reciprocal space is three-dimensional. You have this wants to indicate the iso-intensity lines. It is a three-dimensional object in reciprocal space, and line profile is the integrated intensity distribution parallel to the diffraction vector. Therefore, the intensity distribution has to be integrated over the directions perpendicular to the diffraction vector. Now, the integration can be somehow visualized in this graph. This is the incoming beam direction. These are the reflecting planes. This is the fold plane. This is the streaking in the triclinic system. And the line profile is obtained if we integrate around the fundamental reciprocal lattice point in the direction perpendicular to the G vector, somehow in this direction. If I blow up that part, the integration in this direction. The transformation between L and G, that means the triclinic system and the diffraction vector direction, to a very good approximation, is given by this formula, which we have seen actually. No, we haven't seen that. So this is the tricline full width half Mach, which can be transformed into the diffraction vector direction by a simple linear formula in front of that quantity, which contains the HKL dependence. This has been shown for the closed back planes by Welterop and co-workers. Estevez Rans have also done some fundamental work in this direction, and the third one is from my PhD student. Here I want to show you these transformation four factors for the four most common pyramidal planes on which twinning occurs in magnesium, titanium, zirconium, these very important structural materials, where always the triclinic full width half Mach is of this form. Again, we come back to that. Now, this is already the transformed pattern. So this is the diffraction pattern which you can measure in a diffraction experiment. It looks very similar to the one in the triclinic system, but it is not identical. And this I would like to show you in more detail. Along the streaks, as I mentioned before, there is no HKL dependence up to the asymmetry. The HKL dependence of line broadening is introduced by the L into G transformation. The resultant or measured profiles are the sum of the subprofiles corresponding to one reflection. You can do that either by taking one HKL index. This is for an FCC. This cartoon is shown for an FCC case. You can take a reflection index 311 and put the fold planes into the different positions, into the different directions, or you take one fold plane and calculate the effect in the different directions. This is a cartoon showing what happens if you have intrinsic stacking faults on the 111 plane in an FCC crystal. If your fault is 111 and your subreflection is 3,1 minus bar 1, then the sum of the HKS is 3, and this we learned from the book of Warren, that in this case the twin or the stacking fault will not have an effect on the line profile, and we obtain an almost, in principle we get a delta function, which is convoluted with the instrumental effect, or with, well, in the kinematical approach it is a delta function. If the subreflection is 3 minus 1 minus 1, then the sum is 1, and then there is an effect. And if it is a stacking fault, not just a twin, then beyond the broadening, you also get a shift. This is also well known. This you can find in the book of Warren. If the subreflection is 311 for the same twin direction, 111, the sum is 5, and you get a broadening in the other, a larger broadening and a shift in the opposite direction. And the beauty of this effect is that if you take a higher harmonic of the same reflection, let's say if you could measure the 622, then the shifts would be reversed in the other direction. This is the result. The black curve is what you expect to be measured, and the blue, green, and red are the subreflection profiles. Now let's come back to hexagonals. Here I would like to show you the HKL dependence of twinning on the pyramidal planes. If the reflection, if the subreflections, and if the reflection is 114 and the twin plane, the subreflections in the 114 powder reflection, if the twin planes are 102, then these three subreflections will have these different broadenings, and your net diffraction profile in a powder diffraction measurement will have this broadening, whereas if the twin plane, again 3% of twinning on this plane, then you can all see that the broadening here is much smaller. So from the broadening, you can actually also decide on which plane is twinned. The scale in these two figures is the same. It starts from the same and ends at the same. So these are comparable. Now let's go to another representation. Now let's take the same reflection where the twinning occurs on this pyramidal plane and this pyramidal plane, and let's see what happens if the twin density on both planes is the same, and we take this reflection. You see that on this twin plane, the broadening will be much larger than on the 10.1 twin plane in this reflection. Now let's switch from this, for the same twin planes, let's switch from this reflection to this reflection. Then what happens is that the difference is much larger between the two. And if we go to the third plane mentioned here, 21.0, then the two profile functions will coincide. So it means that there is a nice play in the HKI dependence of the effect of twinning, which is the basis for determining the twin density and the quality of the twinning planes. Again, back to that graph with how the line profile analysis is working. Now, the profile functions for planar folds can be produced on the basis of what I've told you before as this sum, where I sub L, HKL, are the profile functions of the subreflections in a powder pattern. And you have a weighting factor here, which is closely related to the permutation number within the powder diffraction reflection. And of course, you have to separate out the delta function part, which are the cases where the twinning has no effect on line profile, on the line broadening, as I mentioned before. Okay. The broadening and the shifts can be parameterized, and these parameter files can be easily incorporated into a software which will work for your line profiles. Let me show you just very briefly one or two examples. This shows the if you take Inert-Gas condensed nanocrystalline copper, then in the TM micrograph you see dislocations and twin folds. You can see these beautiful twin lamellae. The scale here is 100 nanometers. This is the diffraction pattern, relatively narrow peaks, but still you can extract the dislocation density and the twinning activity. This is just to show you that there is a good match between TEM size distribution and X-ray diffraction size distribution. And this is the conclusion of this exercise. If you plot the twin density as a function of the, let's say, the crystallite size, then you see that as long as the crystallites or the grains or the subgrains are large enough, there is no twinning. That copper doesn't twin. But as the crystal size goes down below about 40 nanometers, then the twin density starts to increase strongly, because to create a dislocation needs a much larger energy. One second example, and with this I would like to finish. The sintering of nanocrystalline silicon carbide at 1800 degrees centigrades at 2 gigapascal pressure and at 8 gigapascal pressure. In the lower pressure case, you see strongly twinned grains, nanograins. They are 100 nanometer or smaller, whereas in the larger, higher pressure grains, you see no twinning. And this was already, this was confirmed by the X-ray diffraction experiments. This is a Williamson hole plot, which gives you a very good idea of what is happening in your material. You have the full width half max in 1 /nanometer scale, and this is actually the diffraction vector coordinate, again in 1 /nanometer. And what you see here is that the upper harmonics have no extra broadening. You have practically a horizontal, no strain Williamson hole plot, although there is a huge jump up and down of the full width half max. This is the HKL dependence produced by twinning. And with this, I would like to finish. This shows how we managed to make a three-dimensional pattern of the effect of twin density as a function of sintering pressure and sintering temperature. Let me finish with this slide. These softwares, they are not on your stick, but they can be downloaded from the internet. These are the web sites. I would like to thank my co-workers. All of these, the first two used to be my PhD students. The last one is my colleague for the last 40 years. And with this, I would like to thank your attention.
Thank you, Tamás, very much for a very detailed talk that complemented, as you said, very nicely what Matteo had led into. So the paper is now open for questions from the floor.
Thank you very much for a very nice talk. Structurally and microstructurally